Hello everyone, my name is Pavel Tsoi and I'm a student from Pattern Recognition and Machine Learning Laboratory of Artificial Intelligence Department. And today my presentation will be about sleep stage classification. This is my contents page, and first I want to talk about what sleep staging is. Then I discuss some methods in machine learning which are used these days for solving this problem. And I will talk about their architecture, their pros and cons. First of all, sleep monitoring is important for every human on this planet, since everyone is sleeping sometimes. And in order to diagnose some problems which are connected with sleep or check the quality of everyday sleep, we need to monitor sleep behavior. This is a scheme of how sleep signal data is acquiring, and then after feature extraction, the data is analyzing, and then it can be implemented in medicine or in daily life. So in medicine it can show to doctor which disorder we have, and in daily life we can check our quality of sleep. Sleep data is acquired by using so-called polysomnogram, which means data from multiple sources such as electroencephalogram or EEG, which is electric waves of our brain, which can be collected by brain-computer interface, or BCI, EOG, or electrooculogram, which connected with eyes and measures the amount of eye movements, and our ones. But nowadays, the most important source for sleep staging is EEG. After collecting the signal data, it is divided into segments of 30 seconds. Then these readings are collected, and the next step is to call sleep specialist to divide segments into sleep stages. Sleep stages themselves are divided into wake stage, OW, rapid eye movement stage, or area, and non-rapid eye movement stages, and 1 and 2 and 3 and 4. Here the deeper stage has the higher number. The classification is conducted using the set of rules as American Academy of Sleep Medicine rules. It takes a lot of time for a specialist to classify the data because the data is acquiring during the whole night. Thus, the machine learning methods were introduced as an alternative to do automatic classification. But there are some issues with them. First, the data is very imbalanced. For example, wake stage, or W, and N2 stage, or non-rapid movement second stage, and rapid eye movement stage data have much more samples than in other stages. Thus, even high accuracy doesn't mean good classification in sleep stage classification. That is why in sleep staging, F1 metric is used more often. Although unlabeled data is very easy to produce, we only need one BCI interface and can do it in any hospital or even home. But another problem is the lack of data which is already classified due to the time-consuming nature of classification process by human, because the data is from 6 to 9 hours. The main ideas to overcome these issues are self-supervised learning in order to learn some inside patterns of our brain sleep signals, and our idea is to use data augmentation to provide more learning samples. First of all, let's look at the one model for solving sleep staging. The name of this model is time series representation learning via temporal and contextual contrasting, or simply TS-TCC. The main idea of this model is to provide generalized framework for all time series representation using both temporal contrasting and contextual contrasting. Contextual contrasting here was inspired by computer vision tasks and tries to maximize a similarity between two representations of the same sample. Temporal contrasting is using the temporal information or information connected with time of previous samples and compare it with the next one, which is natural due to the fact that we are working with time series. You can see it here. First, if you look at the architecture, the model takes two augmentations of a signal, then encode them, and trying to predict the future parts of a signal from previous signals, and compare it with another augmentation result, so here and here. As you can see here, this comparison uses temporal loss. I'll talk about it later. And that the two representations are compared between each other here for contextual contrasting. Now I'll explain all three parts separately. Let's start with data transformations, or time series data augmentation. First, authors of this model suggested that using two different augmentation views can improve representations and their robustness. That is why we are using so-called weak and strong augmentation view. Weak strategy was inspired by jittering and scaling from computer vision, when you scale and jitter or shake the original image. So in time series sense, they are adding some random variations, which is kind of jittering, and scaling the magnitude. Inspiration for a stronger augmentation came from permutation and jittering. Thus, for time series, we need to split the signal into some segments and then rearrange them, or in other words, just shuffle them, and lastly add some jittering. So as I said before, here it is to add some random variations. Then we have one encoder which with 3-block convolutional architecture, which looks like that. It's just simple convolutional encoder and nothing special here about it. Next, let's discuss temporal contrasting. First, we get encoded representation of X, which is described by letter Z. Then we got context vector CT by using autoregressive model, which is transforming in this case. Here we are analyzing all previous representations, so till this moment. Next, we need to describe our temporal contrasting loss, which is here for strong and here for weak augmentation. As you can see, context vector of weak augmentation here is compared to a strong representation and vice versa. One last thing I need to say about this loss is that we are using WK, linear function mapping, in order to keep dimensions of C and Z the same, so we can have different dimensions. Let's look a little bit more at our autoregressive model architecture. Here we are using transformer, and first we concatenate existing context vector with prediction of previous representation. Then we normalize it and pull through multi-head attention. Then we add here skip connection and then normalize it one more time and set it into MLP or multi-layer perceptron. One more time adding skip connection, and the output of this block becomes the new context vector. On the formulas it will be seen like that. So concatenation, then multi-head attention, normalization, skip connection 1, 2, and new context vector. However, it's worth to mention that the model uses 6 transformers in a row. So L here, this L, is the current layer of transformer. Next, we compute simple contextual contrasting loss, which is using cosine similarity, as you can see here. After all, we have our big overall loss, which consists of 2 parts, temporal part here and contextual part here. These lambda parameters are just variables and can be chosen arbitrarily. Lastly, let's look at the pros and cons. As you can see, this model considers temporal information, which is very important for any time series, and sleep staging data as well. And actually shows good performance not only with sleep staging but also with our applications with time series. Also, It outperformed all existing before state-of-the-art methods for sleep classification, and has better performance on a limited data training when we fed only a little amount of data in checking results. The main cons of these models are using the permutation method, because such thing can disrupt sleep data because it's time series, and permutation can change the reality at all. Lastly, although it has better performance, this model still cannot deal with imbalances, and using it in real life will result in many misinterpretations. For future research, I consider to search for more generalized approach dealing with time series and to find out how to deal with this data set imbalance. This is the references page, and thank you for your attention. You can ask your questions in comments. Thank you.